Uh, mm. Okay, so so where was I? So last time, we talked about the increasing sequence. Suppose that your sequence is increasing, and so it's well as index goes up, so if the number also increases, and if your sequence is bounded above, then you see increasing sequence cannot blow up to the positive infinities. Therefore, it is very reasonable to assume that you, in that case, my sequence must have some limit underneath. This is what we are trying to prove for today's lecture. Okay. Uh, so I have a sequence, and this is an increasing, and say that this is this is bounded above. Above sequence. And I want to say introduce a subset of real numbers. Defined like this. So what is this? So this is a collection of all terms that appears in the sequence. And this is a subset of real numbers. And I want to say that clearly this is a non-empty subset, right? Which is obvious. And also, this guy is bounded above. Why? Because the sequence is, well, prohibited from exceeding some certain point. Therefore, my subset S must have an upper bound, right? So this is non-empty and bounded above. Okay, so speaking of non-empty and bounded above set, yeah, I feel like I will need to use the axiom of the least upper bound, right? So I told you that the axiom of the least upper bound is that makes the striking difference between the set of all rational numbers and the set of all real numbers. And since this guy has non-empty and bounded above, therefore, because of the least upper bound axiom, so I can say that there is a least upper bound of this set. Now, what I want to show is, I want to show that L is actually the limit of the sequence. Okay. Now, to show that for any positive epsilon, and if I can find the integer n satisfying the blah 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 criteria condition, then we are done. Okay. Now, okay. All right. Well, L is the least upper bound, so that means for the every element in this subset must be less than or equals to this number. because L is an upper bound, and also L is the least upper bound. That means any number that is slightly less than L cannot be an upper bound, right? So L minus epsilon cannot be an upper bound, right? So, and in other words, a number is not an upper bound of this set, implies that you must be able to find some number, some point from this set, and that point must be strictly greater than this guy, right? So is not an upper bound of S. So that means there is a number which I will call A of n from S such that L minus epsilon is greater than A n. Okay. Now, this number obtained from this guy, and that number must be, is called an, and any index greater than this guy, then what happens is, we know this, and since my sequence is an increasing sequence, therefore a small n must be greater than equals to a large n, right? Because of this index. And at the same time, an is number from this set, therefore, and since L is an least upper bound of this guy, so L must be greater than or equals to an, right? But this is also less than L plus epsilon. Okay, yeah. Since, even though I have many inequalities, but the point is A minus n minus L is less than epsilon. Because this middle guy lies between L minus epsilon and L plus epsilon. Okay, so what is this? So for any epsilon, I was able to find so precisely, yeah, I was able to find a number, large n, such that if any index is greater than this number, then the distance between an minus L is guaranteed to be less than epsilon. So proof is done. Okay, great. I can prove the exactly same thing for the decreasing and bounded below sequence. Well, this time around, let us imagine a decreasing sequence. Sequence is decreasing, but if the decreasing sequence is bounded below, that means even though my sequence is decreasing, but my sequence cannot go to negative infinity. In that case, such a decreasing bounded below sequence must have a limit somewhere above this limit, right? Somewhere above this lower bound, right? So I can prove the same thing for, so therefore, I'm okay to say that every decreasing bounded below sequence should be convergent. I can prove this using exactly same argument as before. So yeah, I won't spend enough. Also, I'm gonna omit this. And so combining this statement and that statement, we can summarize everything into this one single line. No. Okay. So this is so-called the monotone convergence theorem. And bounded monotone sequence. Okay, do you remember the definition of the monotone sequence? If a sequence is either increasing or decreasing, then we say that it's a monotone sequence. And if an increasing sequence bounded above or the decreasing sequence bounded below, then these guys must have limit. So this is called the monotone convergence theorem. This theorem is so widely used in the freshman calculus, so we gave this guy a name. So from now on, whenever I say, because of the MCT, then you should remember the monotone convergence theorem. Okay. Let me try to remember this sequence, which was given by recurrence relation. And S1 was 2. Do you remember this? Well, this was known to be converging to square root of 2. And we were able to prove that this guy was converging to square root of 2 by using the squeeze theorem, I remember. Yeah. But this time around, I'm going to show the convergence of this guy by using the monotone convergence theorem. First, you have to remember, because of the arithmetic and geometric inequality, we know that the sequence is always greater than or equals to square root of 2. Sn is greater than square root of 2. Because the right-hand side of this equation is defined by the arithmetic mean of these two numbers. Okay. So this is always greater than equals to square root of 2. Okay. Now, I want to take a difference between two consecutive numbers, Sn plus 1 minus Sn, which is this guy. Simplifying this is negative 1 over 2 Sn plus just 1 over Sn. This is minus 1 over 2 times Sn by Sn squared minus 2. First, this factor. So we know that Sn is always greater than equals to square root of 2. So this first factor is known to be positive for or n. And for this factor, we also know that this guy is always non-negative. So this is so combining with this negative sign, so everything is non-positive. So less than equals to 0. So Sn plus 1 is always less than Sn, less than or equals to Sn, right? So this implies that the sequence is decreasing sequence. And also, because of this is bounded below. Now, by the monotone convergence theorem, the sequence has a limit. even though the monotone convergence theorem is very important, but it does not tell us the precise value of your limit. So it only tells us there is such a number. So in order to tell, so what remains, therefore, what remains to show is, in order to show that this guy is converged to square root of 2, then we will need to show that this number is actually square root of 2. How? By taking the limit to the both sides of this recurrence relation. We take a limit. This is what? N to the infinity. Therefore, we know that this number is tending to S. And on the other hand, this number has this sequence has a limit, and this sequence has a limit. And the right-hand side should be tending to 1/2 times S plus 2/S, right? Here, so we are using that. Well, you have to remember that if a sequence is convergent, then the reciprocal of the sequence also must be convergent. So I'm taking advantage of the theorem. So S is 1/2 times S plus 2/S. We have just ended up with this quadratic equation. This quadratic equation is going to be can be simplified to S squared is 2. Well, in principle, S could be plus or minus square root of 2, but in this case, S equals to -2 doesn't make sense because, well, all these numbers are positive numbers, therefore, limit is negative, doesn't make sense. So only reasonable answer should be S is plus square root of 2. Okay. 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 Probably. So we are studying the many sequences, but probably the one most important sequence is the geometric sequence. So in Korean, the 기하수열. Okay, you know what I mean? Yeah. The geometric sequence is given like this. So suppose I have a sequence, and if the ratio between two consecutive terms is a fixed number, then we say that is a geometric sequence. So in other words, if an plus 1 over an is always some fixed number, then an is called a geometric sequence. And this number is called the common ratio, or whatever it is. Yeah, I don't know. Yeah, that's fine. So this is a geometric sequence. And we also have this theorem for the geometric sequence is we have a geometric sequence that looks like this. And if the absolute value of the common ratio is less than 1, it should be tending to 0. And if the common ratio is 1, it's tending to 1, and otherwise divergent. Do I have to prove this? No. Yeah. Okay. So let's take this for granted. Mm. Mm. Uh, this exercise tries to figure out the competition between the exponential function and the factorial functions. Have you ever wondered which one is increasing faster than the other? Well, but if you spend it is not very hard to say that factorial function is increasing way faster than the exponential function. Yeah, exponential function is already increasing incredibly fast speed. But however, exponential function is still, and so b to the n is a function obtained by multiplying same numbers on and on. Multiply by b, multiply by b, multiply by b. But on the other hand, the factorial function is obtained by multiplying by 1, multiply by 2, and multiply by 3, and so on and on. So therefore, eventually, no matter how large your common ratio is, eventually factorial function will win over the exponential function. Okay. So therefore, this theorem, this exercise actually tells us the factorial increases way faster than the exponential. But this will also require a justification. So let's try like this. We choose an integer. We choose an integer n such that no matter how large your common ratio is, but you can always find such an integer n, right? Now we define a number r to be the absolute value of b over n plus 1. The point here is this number r, this is clearly first, this is positive number, and this number is less than 1. Right? Because n was already greater than absolute value of b, therefore n plus 1 must be also greater than a. So, now for any integer n greater than this guy, so there is a positive integer k such that n is large n plus k. So k should be understood as a difference between the large n and small n. Right? Now, b to the n over n factorial and bn n factorial times b n plus 1 times b n plus 2 times b over n plus k. I can rephrase this factor fraction into these fractions. Okay, so this is the definition of the factorial function. And n plus k equals 10. Yeah. So okay. So yeah, I factor this single fraction into these many fractions, and this number is less than equals to r. And same thing is true for this number. This fraction is also less than equals to r, right? Because the denominator is greater than this, so therefore this guy is less than r, less than equals to r. And likewise, this everything is less than r. So b to the n's over n factorial times r to the k. Because yeah, since I have k such numbers and they are all less than r, so therefore everything is bounded by this. Okay. Now, as n to the infinity, b to the n over n factorial, this is less than equals to b to the n over n factorial times r to the k. Okay. First, you have to remember that this number, large n, is a fixed number. So once I have chosen this n here, then this n doesn't change. So therefore, for this first fraction is a fixed number. This is constant. And as n to the infinity, as n goes to infinity, then k also goes to infinity, right? So eventually, this is constant, and this common ratio is known to be less than 1. Therefore, everything will go to 0. Okay. So this guy also goes to 0. Okay. All right. Okay. And today, we want to talk about the series. You know the difference between the sequence and the series. In Korean 거기 sequence는 이제 수열이고 series는 급수죠, 그렇죠? 네. 급수. 네. Okay. Well, in order to define a series, then first of all you have to have a sequence, which I will call AN, and from this given sequence you can make whole new another sequence, which is called a sequence of the partial sum. Or sometimes I just say a partial sum sequence. Partial sum sequence is defined like this. S1 is just A1. S2 is A1 plus A2. And Sn is A1 plus A2 plus all the way up to An. So Sn is just nothing but merely taking the summation from A1 to An. So this is, so I can make another sequence called a partial sum sequence, or the sequence of partial sum. So this is the part, and so this Sn is called a partial sum sequence of the series of this guy. And if the partial sum sequence is convergent, and we define the series is convergent. And in this case, this limit is defined to be the limit of this infinite series. So in this case, if Sn is convergent, then we say the series is also convergent. Otherwise, this is divergent. Okay, so this is it. So what do you think about this so-called infinite series? Yeah, even though infinite series looks like way more complicated than the sequence, but actually, in terms of the pure mathematics, they have no difference. I mean, sequence and series, they are only differs by their names. But why? Because convergence or divergence of sequence, convergence or divergence of series is merely defined by convergence or divergence of the partial sum sequence. So if you understand the convergence or divergence of the sequence, then you're done about the series. Okay, good. Then why do we even need to care about the series? I believe the reason that we are interested in the series is this, because later on, you're going to study, you're about to introduce many interesting functions and many interesting numbers. And most of times, these numbers or functions are defined by, not by using series, but given by series. So in order to work with them properly, then we will need to build up some very interesting tools on the infinite series. Okay, but I mean, the point is, don't be afraid about the series. They are very easy. Yeah. Okay, and what you're gonna do is this. So given any series, first of all, our final goal is, given any infinite series, we wanna compute the exact precise value of the series. But before we do that, the first question is, if any given series is convergent or divergent. Okay, I mean, so suppose that you are working with a series which is divergent, but if you struggle to find a number for the divergent series, then that will be a huge waste of time. So instead of trying to find out precise value of the series, then I strongly recommend you to determine whether or not if any given series is convergent. Okay, but being able to determine if any series, the convergence or divergence of series, turns out to be somehow complicated than the convergence or divergence of sequence. Because of the harmonic series. I mean, our prime example would be a harmonic series. You know harmonic series, right? 조화급수, right? So 1 plus 1 over 2 times 1 over 3rd plus 1 over 4th, and 1 over n. So it's basically adding up a bunch of 1 over n, 1 to infinity. And is it convergent or divergent? You know? Yeah, absolutely that is divergent. And we know the number is divergent, but so technically speaking, so you can make it arbitrary, you can make it greater than any number you like. So you can make it arbitrarily large. But this increasing speed is very slow. I mean, incredibly slow. What I mean by this, if you want to make your harmonic series to be greater than, say, 4, then I guess you will need just couple of main terms too. Couple of main terms, right? Just 1 plus 2. If you add up like this, maybe 10 terms, 10 first terms, then that number would be greater than 4. But if you suppose that you want to make your harmonic series to be greater than, say, 100, then how many terms do you think you will need for that? The answer is you're going to need 10 to the 43 many terms just to make it greater than 100. Okay, so its speed is incredibly slow. So therefore, if you do not know the harmonic series is divergent a priori, then you might be suspect, oh, this increasing speed is so slow, so I suspect that would be somehow convergent. So just being as well, so that means just by looking at the speed, well, increasing or decreasing speed of the series is not suffice to tell whether or not if any given series is convergent or divergent. So for today, so we're going to study many interesting criteria to tell, well, the convergence of the series. And the first theorem, the first criteria, I guess this guy is the easiest. It's called the test for divergence. It goes like this. I have a series, AN, and suppose that this guy is convergent. then the sequence that was used to build up this infinite series should be tending to 0 as n to the infinity. This is the test for divergence. Yeah, this guy also looks very obvious to us, because infinite series is basically about adding infinite many numbers. And if this adding numbers is not tending to 0, suppose that this guy is tending to 1 over a million. Even if this guy is that small, but eventually you're going to end up some non-trivial number infinitely many times. Therefore, the series cannot be convergent, right? The proof is also very easy. Since we are assuming that the series is convergent, that means this partial sum sequence, I'm going to use another index, 1 to n. This partial sum sequence must be convergent. So this is S. Then limit of an. But an is always can be written as a Sn minus Sn minus 1. But this guy is converging to S, and this guy is also converging to S. Therefore, should be 0. Okay. Yeah, I know this test, the test for divergence, is very silly, but it gives us the first criteria to tell if your series is convergent or divergent. For instance, take a look at this series. Yeah, even though this one looks somehow scary, but this is clearly divergent. All right. And as you know well, the converse of the theorem is not true. Right? For instance, like harmonic series. 여러분들 컨버스가 뭔지? 컨버스가 역명제고요. 수학에서 뭐지? 까먹었어. 그다음 이명제가 뭐 있지, 그치? 영명제랑 이명제 혹시 아세요? 이명제는 인버스라고 하는 것 같고요. 대우명제는 contrapositive라고 하는 것 같아요. 네, 갑자기 생각나서 말씀드렸어요. 네. 죄송합니다. 네, 제가 영어 그렇습니다. theorem is not true. For those of you who have never tried to prove that harmonic series is divergent, yeah, this is probably the easiest proof. Yeah, I think harmonic series is probably the most important series other than the geometric series. Well, because 1 plus 1 over 2, 1/3, 1/4, and 1 over 8, 1 over 9, 1 over 16, and this is less than 1 over 2, and grouping these two terms, and this is less than 1/4, and this is also less than 1/4. So, and we have two numbers that are less than 1 over 4, so they are less than 1 over 2. And now we have 4 numbers, and each of these numbers, they are less than 1 over 8. So therefore, combining them, they are all less than 1/2. And now we have 8 numbers, then they are all less than 1/16. So they are also less than 1/2. So this is the why. This is the reason that why this guy must be divergent. Okay. All right. And the next, the geometric series. This is the geometric series. So as you can see from this definition, the geometric series is obtained from the geometric sequence. And if the common ratio of the geometric sequence is less than 1, the absolute value of the common ratio is less than 1, then the geometric series is converging to this guy and otherwise divergent. I don't think I will need to provide the proof of this guy. Right? You guys all know this very well. So, for instance, so this infinite series is converging to, so the common ratio is 1/2, which is definitely lies between -1 to +1. So it is converging to 2. So in other words, so if you have a tree that grows 1 meter for first year and 1.5 meters second year and 1.25 years in third year and so on, then eventually the tree will be growing up to all the way to 2 meters. Okay, all right. Now what I want to study is slightly complicated than this one. Now I am interested in this series, 2n plus 1. What do you think about the convergence or divergence of this series? This is not a geometric series, right? But I have very strong feeling that this guy must be convergent. Okay, this is my justification. At the very beginning, so they look quite different, but as n goes to some arbitrary large number, then just comparing the denominator with this guy and that guy, I mean, they are almost the same thing. 2 to the 1 million and 2 to the 1 million plus 1, I mean, they are no different to each other, right? So, I mean, eventually, this guy, this series will behave just like this geometric series, right? And since we already know this guy is convergent, therefore this guy also must be convergent. Okay. But how do I prove this? Being able to prove is completely different. Completely different idea. Require completely different idea. So, because of this, in order to show that this guy is convergent, so I will need to introduce probably the most powerful theorem that gives us criteria whether or not any given series is convergent. This is called the comparison theorem. Okay. I have two sequences, AN and BN, and from this, two sequences, I was able to make two different series, AN and BN. And I wanted to emphasize that the sequences involved in these two series, they must be all non-negative. Right? They are all greater than or equals to 0. And assume that AN is less than or equals to BN. Okay, all right. Under this hypothesis, and the claim is this. If the greater guy, and so greater guy convergent, then the smaller guy should be also convergent. Because, well, so this guy is convergent. That means this guy will be converging to the partial sum sequence made from this guy. And okay, so therefore, partial sum sequence of this series cannot exceed the limit of this guy, right? And the thing is, since all the terms involved in this series is they are all positive, therefore, this is very important observation. The partial sum sequences from this series must be increasing sequence, right? Because the partial sum sequence is obtained by adding bunch of positive numbers, non-negative numbers. Therefore, partial sum sequence of this guy should be always increasing. Therefore, increasing and bounded above, therefore, must be convergent. Okay, so yeah, I already spoken out all the ideas involved in the proof. But anyway, this is the proof. By the way, I want to introduce this. I think this is the right time to introduce this notation. This notation represents this guy is convergent. Less than infinity. So this means this is convergent.
원래 저렇게 쓰는 거예요?
예, 맞아요. 되게 자주 사용하는 노테이션이기 때문에 이게 제가 인트로듀스 할게요. 예. 그러니까 특히 파지티브 텀가 뭐지? 파지티브 텀 시리즈에서는 되게 자주 사용하는 노테이션이에요. 그러니까 파지티브 텀 시리즈는 수렴하지 않으면은 언젠가 이제 파셜 썸 시퀀스가 무한으로 터질 거 아니에요, 그렇죠? 그래서 근데 무한으로 터지지 않으니까 수렴한다는 뜻이죠, 그렇죠? 예, 좋은 지적이에요. 예. So Sn is the partial sum sequence from this series is from J1 to infinity, Bj is convergent. So, and remember last time we said that every convergent sequence is bounded sequence. So that means there is a number, positive number, since this is this is increasing and non-negative, such that bounds all the partial sum sequences. So this is the partial sum sequence from series AN. And comparing this with this partial sum sequence, this is greater than Bj. And this is my Sn, and we know that Sn is bounded by L. Okay, good. So, and this partial sum sequence this is increasing and bounded above. This is increasing and bounded above. Therefore, is also convergent. Okay, good. All right. So let me go back to the original exercise that we were interested. So I have this series, which is 1 over 1 plus 2 to the nth. This is convergent because this guy is less than 1 over 2, 1 over 2 to the nth, and these two numbers, they are also greater than 0. And since this guy and the series made by this guy is known to be convergent, therefore, this is also convergent. Okay. Okay. By the way, for those of you who might be bothered by the starting point of these series, I mean, yeah, clearly the theorem is stated when the first index is 1. But here, I am freely using the comparison theorem for another starting point of these series. But don't worry about that. Because, well, if you are wondering about the precise value of the infinite series, then the starting point may be an issue. But in this case, since we are merely discussing the convergence or divergence of the series, and convergence or divergence of any given series is not affected by first few finite remaining terms. It is only affected by infinite remaining terms beyond that. Therefore, okay, don't worry about the starting point. Okay. This time, now we are interested in the convergence or divergence of this series. What do you think about this series? Is it convergent or divergent? I also have very strong feeling that this guy should be also convergent because of the same reason. Comparing this guy with this series, they are almost the same thing. Well, because this -1 effect has almost no effect when n is a large number. So therefore, the behavior of the series must be very much like to the behavior of this guy. So therefore, and this guy is convergent, so this guy must be also convergent. But the problem is this. So I want to show that this guy is convergent but I cannot use the comparison theorem. Why? Because in order to show that this guy is convergent by using comparison theorem, then I will need to compare this guy with another C series bigger than this one. But this guy is not bigger than this. Now, then, how do I fix this? If you really want to use the comparison theorem, then there is a way. Well, you can try to maybe you can rely on a little bit complicated, not complicated, but you can rely on some little bit more algebra, and you can still use the comparison theorem to show this. But for this time, I want to introduce slightly stronger version of the comparison theorem, slight variation of the comparison theorem, which is called the limit comparison theorem. And this is even more stronger and even more versatile than the naive comparison theorem. And it goes like this. Okay. I have two series, AN and BN, and both of them, they are series of the positive terms. In other words, these two sequences, AN and BN, they are all non-negative numbers. So as we just like the comparison theorem, this limit comparison theorem is only working for series of the positive terms. Okay, so in that means if your series involves some negative numbers, then you may not be able to use a limit comparison theorem. Anyway, suppose that now for this time we are interested in the another sequence AN over BN. Another sequence made by the ratios between AN and BN, and if the limit exists and should be is a positive number. This is the hypothesis. Well, suppose that this guy, the limit of this guy exists. And these numbers, this is positive and this is also positive. So these two numbers, so therefore this number is positive number. But limit of positive sequence may not be positive, right? It could be 0, right? And this hypothesis says that this limit should be a strictly positive number. So this is very important criteria. Okay. Anyway, suppose that all these assumptions were satisfied. Then this guy's converges if and only if this guy converges. So in other words, if this guy is convergent, then this guy is also convergent. And if this guy is convergent, and if that guy is also convergent. And if you take the contrapositive of the statement, that means if this guy is divergent, then this guy is also divergent. And if this guy is divergent, then that guy is divergent. Okay. Well, I would like to say that if all these assumptions are satisfied, then these two series, they are sharing the same fate, same destiny. All right. Okay. Okay. Proof. Since we are assuming that the limit of this guy exists and positive, so I'm going to say that limit R. Okay. So this is the convergence of the sequence, not a series. So I will need to use the epsilon n argument for epsilon. For any epsilon, so I should be able to find a corresponding integer n. So this time, I'm going to use this guy to be my epsilon. Yeah, the epsilon should be a strictly positive number. So for this given r, I divide it by 2, but this is still positive, so this is going to be my epsilon. Now for this epsilon, well, since this guy is convergent, so I should find a number, integer n, such that if the index is greater than this guy, then an over bn minus r should be less than epsilon. Or in this case, my epsilon is just out of it. Okay. Okay, this final inequality can be written as an over bn minus r minus r over 2 and r plus r over 2. Yeah, sorry. I will just say this is R over 2 and 3R over 2. Okay. So if index is greater than this, then well, we have these two inequalities. Okay. So this is an if and only if statement. So I will need to prove the both directions. I will prove this implication first. Okay. Now we suppose that is convergent. Then for any index greater than this number, or any index greater than this number, then I have these two inequalities. But for this time, I only need this guy. I only need this guy. So R over 2 is less than AN over BN. But in other words, this is R over 2 times BN is less than AN. Okay, so since this index is only valid for, so this inequality is only valid for the index greater than this. So yeah, I will restrict my value of the index from n plus 1 to infinity. So R over 2 BN, this is less than AN. Okay. Okay, now I am using the comparison theorem. Since we know that this guy is convergent, so this is also convergent, right? And by the comparison theorem, so this one must be also convergent. And multiply by this is some constant, right? Multiply by constant, it does not affect too much. So this is also convergent. Therefore, so since this is convergent, so therefore, from 1 to infinity, this is also convergent. All right, for the another way, another direction. Now we suppose that from 1 to infinity, Bn is convergent. Okay, so by using the same trick, if n is greater than n, then now we have these two inequalities, but this time around, I'm going to use this one. AN over BN is less than 3R over 2. So then AN over BN is less than 3R over 2. This which is, in other words, AN is less than 2, 3R times BN. So from n plus 1 to infinity, AN is 1 to infinity times 3r over 2 times Bn. Okay, and since this guy is convergent, therefore, the same series but multiplied by another constant also must be convergent, right? So therefore, this is also convergent. Okay, great. Okay. Now let me go back to the original question. So we were wondering whether or not if the sequence, if the series is convergent. And now I can confidently say that this is convergent because we are taking now I am comparing this guy with this geometric series, and you take the ratio, and the limit of this ratio is tending to is tending to 1, which is strictly a positive number. So that means this guy and this guy, they have the same fate. So since this guy is convergent, so therefore so is this one. And likewise, is this guy convergent or divergent? Even though this guy is slightly smaller than the original harmonic series, but this is still divergent. Okay. Okay. All right. Yeah. Yeah. We have still I have still 7 minutes, but this time is not enough to introduce another theorem. So yeah, I'm really sorry, but let's say this is for today. And see you next time. Thank you. 박수 너무 부끄러워 치지 마세요. 네.